Quite science journeys. High above Earth, far beyond clouds and weather, oxygen does not always stay where we expect it to. We usually think of oxygen as something firmly tied to our planet, held in place by gravity, locked into air and oceans and safely wrapped around Earth like a protective layer. That picture is mostly true, but it is not complete. At the very edge of Earth's atmosphere, the air becomes thin and familiar rules begin to soften. Here some oxygen atoms lose electrons and become charged particles, and charged matter does not behave like ordinary air. Instead of simply drifting with winds, these particles respond to electric and magnetic forces. They can move along invisible paths that do not exist lower down. The fraction involved is tiny compared to the whole atmosphere. Most oxygen remains bound to Earth while a trace becomes mobile at the edge. What moves outward does so slowly, one charged particle at a time. This process has been unfolding for an immense stretch of time. For billions of years, Earth has been releasing small traces of oxygen into near space, one charged particle at a time. Most of that material disperses and fades into the background of space, but some of it follows structure. Earth is surrounded by a vast magnetic environment that extends far beyond the planet itself. On the night side, away from the sun, this magnetic field stretches outward, forming a long tail that reaches deep into space. Within this region, motion is guided rather than random. Charged particles can drift along magnetic pathways instead of scattering in all directions. From time to time, the moon passes through this invisible structure, and when it does, it moves through material that once belonged to Earth. This is how oxygen from our planet can reach the moon. Not as breathable air and not as a steady flow, but as individual ions moving slowly through Earth's magnetic night. We know this because spacecraft have measured these particles directly. Instruments designed to detect charged atoms have detected oxygen ions leaving Earth, and later detected similar ions near the moon's orbit. What seems like empty space turns out to be shaped and active. In this episode, we will follow this quiet connection in 3 clear steps. First, how oxygen can leave a planet with a strong atmosphere. Then how Earth's magnetic environment guides that oxygen through near space. And finally, why traces of Earth oxygen on the moon matter for understanding the lunar surface and its future. The scale of this story is vast, but the process itself is gentle. A slow drift guided by invisible fields linking Earth and moon across deep time. Oxygen feels permanent because we live inside it. Near Earth's surface, air is dense, gravity dominates motion, and molecules collide constantly. In this familiar environment, oxygen appears stable, predictable, and firmly attached to the planet. This everyday experience shapes intuition. We picture the atmosphere as a single layer held tightly in place, with a clear boundary between air and space. That picture works well close to the ground, but it becomes less accurate with height. Earth's atmosphere does not end at a sharp edge. As altitude increases, air gradually thins. Molecules grow farther apart, collisions become less frequent, and motion slows relative to the scale of the planet. At lower altitudes, oxygen moves as part of a fluid. It is carried by winds mixed by turbulence, and bound into a collective system where individual particles rarely act alone. Higher up, this collective behavior weakens. In the upper atmosphere, sunlight carries enough energy to change atoms themselves. Ultraviolet radiation and energetic particles from space interact directly with oxygen atoms. Electrons can be stripped away, turning neutral atoms into charged ions. This transition is quiet and continuous. There is no sudden threshold where air becomes space. Instead, familiar matter slowly enters a different physical regime. Once oxygen becomes charged, its behavior changes in a fundamental way. Gravity still acts, but it is no longer the only influence. Electric and magnetic forces begin to matter, sometimes more than gravity itself. This shift does not affect most of the atmosphere. The overwhelming majority of oxygen remains neutral, bound into air oceans, rocks, and living systems. Only a trace fraction enters this charged state. That fraction matters because it moves differently. Charged particles do not require strong pushes to change direction. In regions where collisions are rare, even weak fields can guide motion over long distances. This is why oxygen is not as fixed as it seems. Stability at the surface does not imply immobility at the edge. The atmosphere becomes more flexible as it thins. Scale is essential here. The amount of oxygen involved at any moment is tiny compared to the total atmosphere. Earth remains wrapped in a thick life-sustaining envelope of air. What changes is not the planet's balance, but our understanding of its boundary. The atmosphere fades into space rather than stopping. At this boundary, time becomes the dominant factor. Individual ions move slowly, but they move continuously. Paths that are insignificant over minutes or hours become meaningful over millions of years. This slow behavior defines the first step of oxygen drift. Before oxygen can move outward, it must first enter a state where outward motion is possible. Ionization provides that state. It allows oxygen to respond to forces that do not affect neutral air. It opens a pathway that does not exist lower down. The key point is subtle. Oxygen does not need to escape in large amounts to matter. It only needs a mechanism that operates steadily over long periods. In the upper atmosphere, that mechanism is already in place. A small population of oxygen ions exists continuously, created by sunlight and energetic particles. These ions form the starting condition for everything that follows. Without ionization, there is no drift. With it, oxygen becomes capable of leaving the familiar rules behind. Earth does not lose control of its atmosphere at this boundary. Instead, it allows a narrow channel of motion to exist, shaped by physics rather than by force. This quiet flexibility at the edge of the atmosphere is the foundation of the Earth-Moon connection that will unfold next. Imagine rising slowly upward from Earth's surface. Below, the air feels heavy and continuous. Motion is shared and everything moves together. As height increases, the feeling changes. The air becomes thin, almost absent. Space opens between particles and silence replaces motion. Here there is no clear line that marks an ending. There is only a gradual release. Matter spreads out and behavior softens. Oxygen still exists, but not as part of a crowd. Atoms move individually, tracing paths that are long and slow. Collisions become rare and direction begins to matter. Light from the sun reaches this region directly. Energy arrives without resistance, altering atoms one by one. Charge appears quietly, without sound or motion you could see. In this thin layer, forces that feel distant near the ground become influential. Magnetic fields extend through the region, invisible but present. Electric fields shape motion gently without urgency. Nothing rushes. There is no flow in the familiar sense, only gradual movement guided by structure. Time stretches here. A journey that would seem trivial on the surface becomes meaningful simply because it continues. This is not space yet and no longer ordinary air. It is a transition zone where Earth's influence fades without ending. In this region, oxygen becomes something new. Not breath, not wind, but a charged particle responding to fields rather than pressure. The motion is faint, almost imperceptible, yet it persists. Above the planet, beyond weather and sound, this slow behavior continues day and night. Particles drift, pause, and drift again. Nothing announces the change. No signal marks the moment oxygen begins to move differently. It simply does. And over enough time, that quiet difference becomes the first step of a journey that reaches far beyond the atmosphere itself. Once oxygen enters a charged state, it does not immediately leave Earth. Ionization changes how a particle behaves, but it does not remove the planet's influence. Gravity is still present. Most oxygen ions remain close to Earth, moving slowly within the upper atmosphere and near space environment. What changes is not attachment, but freedom of motion. Charged particles are no longer limited to the same rules that govern neutral air. There are several processes by which a planet can release tiny amounts of atmospheric material over time. Some particles gain enough energy to move upward gradually. Others are guided sideways or outward by electric and magnetic fields. These processes are continuous and quiet. They do not appear as bursts or events. They exist as background behavior. For Earth, this behavior represents balance rather than depletion. Material enters the atmosphere through geological and chemical cycles. At the same time, trace amounts move outward through slow escape mechanisms. Over short timescales, nothing appears to change. The atmosphere remains thick, stable, and well mixed. Over long timescales, motion accumulates. This is why the idea of drift matters. Drift describes movement that is persistent and slow. It emphasizes direction and duration rather than speed. Individual oxygen ions do not travel far in a straight line. They wander pores and change direction under weak forces. Their paths are shaped more by structure than by momentum. In regions where collisions are rare, even small forces become significant. Electric fields guide motion gently. Magnetic fields curve paths without pushing. Most oxygen ions eventually return. They recombine with electrons lose charge or fall back toward denser layers. Only a fraction continues outward. That fraction is extremely small at any given moment. It does not represent loss in the everyday sense. It represents circulation at the boundary. What makes this circulation important is its persistence. The same processes operate day and night. They continue during quiet solar conditions and during periods of increased activity. Over millions of years, this steady behavior creates a faint population of oxygen ions surrounding Earth. The population is not static. It is constantly renewed as new ions form and older ones disperse. This surrounding region is part of Earth's extended environment. It exists between the atmosphere and interplanetary space. It is shaped by the planet but not confined to it. Oxygen drift feeds this region continuously. It does not require rare events or extreme conditions. It depends only on time and exposure. Thinking in terms of drift avoids misunderstanding. Loss implies decline. Drift implies motion that continues in the background. The rate of drift is small compared to the total amount of oxygen in the atmosphere. Over time, that small rate is what makes the motion measurable. The significance of oxygen drift lies elsewhere. It creates a pathway by which material can leave Earth without disruption. It allows atoms to enter regions where new influences apply. Once oxygen ions drift beyond the dense atmosphere, they become part of a different environment. Here, motion is no longer dominated by gravity alone. Fields and structures begin to guide behavior. This transition prepares oxygen for the next stage of its journey. Drift is not the destination. It is the condition that makes further motion possible. By understanding drift as a process rather than an event, the connection between Earth and its surroundings becomes clearer. Nothing dramatic needs to happen. Steady motion is enough. Oxygen drift defines how material can move outward while the planet remains unchanged at the surface. It is the quiet foundation beneath every later interaction. Without drift, there is no bridge to follow. With it, slow motion becomes meaningful. Picture motion without urgency. Not a stream, not a push, but a slow wandering guided by invisible structure. At the edge of Earth's atmosphere, particles move with patience. They do not rush outward. They explore space gradually. Each oxygen ion carries only a small amount of energy. Its motion is shaped by gentle forces acting over long distances. In this region, direction matters more than speed. A slight curve can change a path completely when followed long enough. Electric fields stretch quietly through space. Magnetic fields bend trajectories without effort. Together they create a landscape rather than a current. Particles drift through this landscape, responding without resistance. They pause where forces balance. They move on when conditions shift. Most of the time, nothing seems to happen. Motion is too slow to draw attention. Change becomes visible only when time is allowed to pass. This kind of movement has no single beginning. It has no clear ending. It continues simply because the conditions allow it. Here, distance is measured in patience rather than speed. Paths form not because particles are pushed, but because they are guided. Drift does not remove material from Earth abruptly. It allows a trace population to circulate at the boundary. This circulation is subtle. It does not announce itself. It exists quietly, sustained by consistency. Above the planet, beyond weather and sound, this motion continues uninterrupted. Day becomes night. Solar conditions rise and fall. Still the drift persists. Over enough time, wandering becomes connection. A particle that moves only slightly can still arrive somewhere new if it keeps moving long enough. This is how small motions accumulate into pathways, not through force, but through endurance. In this slow, structured environment, oxygen prepares for its next transition. Drift sets the stage for guidance, and guidance given time can carry matter far beyond where it began. Earth's magnetic field is often described as a shield. This description is useful but incomplete. A shield suggests a surface that blocks motion. In reality, Earth's magnetic environment does something more subtle. It shapes motion rather than stopping it. The magnetic field begins deep inside the planet. Movements of molten material in Earth's core generate a global field that extends far into space. Close to Earth, this field appears simple. Compass needles align, charged particles curve gently. Farther out, the structure becomes more complex. The magnetic field interacts continuously with particles streaming from the Sun. On the side facing the Sun, Earth's magnetic field is compressed. Solar particles press inward, shaping a blunt boundary. On the opposite side, the field stretches outward. This stretching forms the magnetotail. It is a long extension of Earth's magnetic environment that reaches far beyond the planet itself. Within this tail space is not empty. It contains plasma, a mixture of charged particles that respond strongly to electric and magnetic forces. One of the most important features of this region is the plasma sheet. It is a broad zone where charged particles are more concentrated and motion is organized. In the plasma sheet, particles do not scatter randomly. Their movement follows the geometry of magnetic field lines and embedded electric fields. For oxygen ions that have drifted outward from Earth, this structure changes everything. Instead of dispersing evenly, ions become part of a guided system. The magnetosphere acts less like a wall and more like a landscape. It has channels, gradients, and regions where motion slows or gathers. In this environment, direction is not chosen by momentum alone. It is shaped by the invisible architecture of fields. This guidance does not require strong forces. In regions where collisions are rare, even weak electromagnetic influences dominate behavior. Oxygen ions moving through the magnetosphere are sensitive to this guidance. Their paths curve, align, and adjust continuously. Some ions are redirected back toward Earth. Others remain suspended within the plasma environment. A fraction continues outward along the magnetotail. This behavior has been measured directly. Spacecraft equipped with particle detectors have passed through the magnetosphere and recorded the presence of oxygen ions. These instruments do not infer motion indirectly. They count particles and measure their properties as they pass. From these measurements, scientists can trace where particles originate and how they move. Oxygen ions detected far from Earth carry signatures consistent with an atmospheric source. The data reveal patterns rather than randomness. Oxygen appears where magnetic structure predicts it should appear. The magnetotail, in particular, shows sustained populations of Earth-derived ions. These populations change with solar conditions, but they do not vanish. This persistence indicates organization. Particles are not simply blown away, they are guided and retained by structure. The night side of Earth plays a critical role. Here the influence of the Sun is reduced and magnetic geometry dominates. Motion becomes slower, trajectories lengthen, particles can remain within the magnetotail for extended periods. For oxygen ions, this creates an opportunity. Instead of returning quickly or dispersing completely, some ions remain within Earth's extended environment. This is the missing link between drift and connection. Ionization allows oxygen to move differently. Drift allows it to reach the boundary. The magnetosphere then determines what happens next. Without this structure, oxygen drift would fade into space. With it, motion becomes directed rather than lost. Earth does not simply release particles and forget them. It shapes their paths long after they leave the dense atmosphere. This shaping extends Earth's influence far beyond the surface. The planet's environment becomes larger than the planet itself. The magnetosphere is not a passive region. It is an active organizer of motion. For oxygen ions, it defines where they can go, how long they remain, and whether they encounter other bodies. This understanding reframes the role of Earth's magnetic field. It is not just protective, it is connective. By organizing motion rather than stopping it, the magnetosphere creates pathways. These pathways make it possible for slow drift to turn into meaningful transfer. The magnetosphere prepares oxygen for a journey that would otherwise be impossible. It does so quietly, continuously, and without disruption. This structure is the reason Earth's atmosphere and the Moon can become linked at all. Imagine space shaped without walls. No edges, no barriers, only guidance. Invisible lines curve through darkness. They do not block motion, they suggest direction. Particles move as if reading a map they cannot see. They follow paths defined by balance rather than force. Here motion is patient. A slight curve repeated many times becomes a long arc. The magnetosphere feels vast from within. Distance is not measured by speed, but by how long guidance persists. Charged particles drift along these invisible contours. They slow where fields balance. They move on where geometry opens. Nothing pushes them forward, nothing pulls them back abruptly. Instead, motion unfolds as response, a quiet adjustment to structure. On the night side of Earth, the sun's influence fades. Magnetic shape becomes dominant. Paths stretch outward. Time lengthens. Particles linger, tracing slow loops and gentle arcs. They remain within reach without being held tightly. This region does not feel empty. It feels organized. Each particle occupies a place defined by fields. Movement follows consistency rather than impulse. From a distance, nothing appears to happen. From within, motion never stops. This is how guidance works in space, not by command, but by persistence. Over long durations, structure becomes destiny. A particle that stays guided long enough eventually arrives somewhere new. The magnetosphere does not announce these pathways, it simply maintains them. And within that maintenance, quiet connections form. Motion continues shaped and reshaped until a new encounter becomes possible. This is how space prepares for contact without force, and how slow drift becomes directed movement across vast distances. The connection between Earth and Moon becomes possible because the Moon does not travel through empty space. It moves through regions shaped by Earth's magnetic environment. As the Moon orbits Earth, its path regularly carries it through the extended magnetic tail on the night side of the planet. This passage is not continuous. It depends on the Moon's position, Earth's magnetic geometry, and conditions in the surrounding space. When the Moon enters the magnetotail, it does not encounter a void. It moves through a region already populated by charged particles that originated near Earth. Among these particles are oxygen ions formed in Earth's upper atmosphere. They are not concentrated and they are not moving as a stream. They exist as a faint population drifting within the structured plasma environment. The key to this connection is alignment. The plasma sheet within the magnetotail contains regions where charged particles are more likely to be found. When the Moon passes through these regions, it intersects the slow drift of Earth-derived oxygen. This intersection is quiet. There is no collision in the ordinary sense. The Moon simply enters a space where oxygen ions already move. Timing matters. The Moon does not always cross the same part of the magnetotail. The shape of the magnetic field shifts with solar conditions. As a result, the interaction is intermittent. Sometimes the Moon passes through regions rich in drifting ions. At other times, it passes through relatively empty space. This variability is important. It explains why oxygen transfer is not constant and not uniform. Oxygen does not travel from Earth to the Moon as wind or flow. There is no sustained direction and no continuous pressure pushing material outward. Each oxygen ion follows its own path guided by electric and magnetic fields that define the magnetotail. Motion is gradual, shaped by geometry rather than force. When oxygen ions pass near the Moon, several outcomes are possible. Some continue along their guided paths without interaction. Others are deflected by local electric environments. A fraction encounters the lunar surface. The Moon lacks a global magnetic field. Without this protection, its surface is directly exposed to charged particles moving through space. When an oxygen ion reaches the Moon, it does not slow gently. It interacts directly with surface material, transferring energy and charge. This interaction occurs one particle at a time. There is no accumulation in the way air gathers on a planet. Measurements made by spacecraft have detected increased populations of Earth-derived oxygen ions near the Moon when it passes through the magnetotail. These observations match predictions based on magnetic geometry and timing. This confirms that the Earth-Moon bridge is physical, not conceptual. It operates under specific conditions and follows established principles of plasma physics. The strength of this bridge is not measured by intensity. It is measured by repetition. Each lunar orbit provides an opportunity for interaction. Over billions of years, those opportunities accumulate. A faint transfer repeated countless times becomes meaningful. Not because any single passage is important, but because the process persists. Through this mechanism, Earth's atmosphere, magnetic environment, and the Moon's surface become part of a single extended system. They remain distinct, but they are no longer isolated. This is the moment where slow drift becomes connection. Ionization enables mobility. Drift enables reach. Magnetic structure enables encounter. Nothing dramatic is required. No eruption, no instability, no sudden loss. The bridge operates quietly, shaped by geometry, timing, and deep time. Oxygen that once belonged to Earth can reach the Moon without ever forming air or flow. It arrives as individual ions carrying information about its origin. This is the core mechanism behind the idea that the Moon has been quietly taking traces of Earth's oxygen. Not through force, but through alignment. Not through speed, but through persistence. If you would like more episodes like this, you can subscribe to Quiet Science Journeys. It helps this series continue, and it makes the next journey easy to find. Now let the scene widen again, and stay with that faint motion moving through Earth's magnetic night. Picture the Moon moving silently through darkness. No sound, no resistance, only steady motion. Around it, space is shaped rather than empty. Invisible structure fills the region, guiding particles without touch. The Moon does not seek these paths. It simply crosses them as it follows its orbit. Charged particles drift nearby, moving slowly, guided by fields that extend far beyond the planet below. There is no sense of arrival, only overlap. For a time paths intersect, motion shares space. Then the Moon continues onward. The structure remains, drift resumes. Nothing marks the moment when interaction occurs. No flash, no signal, no visible change. Only quiet contact at the smaller scales. Time stretches here. Each orbit feels the same, yet each passage adds another opportunity. The Moon moves through Earth's magnetic night again and again. Sometimes the environment is rich, sometimes it is sparse. Still the crossings continue. In this rhythm, repetition replaces intensity. What matters is not how much happens at once, but how often it happens. Particles arrive singly, they interact briefly. They leave traces too small to notice in the moment. Yet over immense spans of time, these moments accumulate. The Moon becomes familiar with Earth's extended environment. It records contact without memory or intention. Motion flows around it, shaped by forces that never announce themselves. The scene remains calm, nothing accelerates. This is how connection unfolds in space, not as an event, but as a condition. The Moon drifts onward, carrying with it a surface shaped by countless quiet encounters. And the bridge remains active only when geometry allows invisible unless measured persistent as long as time continues. Here motion does not hurry, it simply continues, and in that continuation worlds become linked. When oxygen ions reach the Moon, they encounter a surface unlike any found on Earth. There is no thick atmosphere to slow incoming particles, and no global magnetic field to redirect them. The Moon's surface is directly exposed to space. It is covered by regolith, a layer of fine fragmented material created by billions of years of impacts and radiation. This regolith is not smooth or uniform. At microscopic scales, it is jagged, fractured, and chemically active. Each grain has been shaped by repeated exposure to energetic particles. Solar wind, cosmic rays, and micrometeoroid impacts continually alter its structure. When an oxygen ion approaches this surface, it arrives with energy and charge. There is no gradual transition. Interaction begins the moment contact occurs. Several outcomes are possible. Some ions strike the surface and rebound. Others lose energy and become embedded in the uppermost layers of regolith. Embedded oxygen does not behave like atmospheric gas. It may bind loosely to mineral surfaces. It may replace atoms within crystal lattices. It may remain trapped within defects created by radiation damage. These interactions happen one particle at a time. There is no accumulation in the familiar sense. Instead, the surface slowly changes through countless individual encounters. The Moon experiences a continuous rain of particles from many sources. Hydrogen from the solar wind dominates. Heavier ions arrive less frequently. Oxygen originating from Earth joins this background. What distinguishes it is not intensity but origin. Each oxygen ion carries a history. Its path reflects conditions in Earth's upper atmosphere and magnetic environment. When it becomes part of the lunar surface, that history is not erased. It is encoded into the chemical and structural state of the regolith. Over long periods, repeated implantation creates measurable patterns, not layers you could see, but statistical signatures distributed across grains and regions. Laboratory analysis of lunar samples shows that the regolith preserves complex chemical records. Different sources of oxygen leave different ratios and binding states. These records do not point to single events, they reflect long-term exposure. In this way, oxygen drift becomes detectable not through quantity but through consistency. The Moon does not receive much oxygen from Earth at any one time, it receives it often. This repeated exposure adds a subtle component to the Moon's surface chemistry. It does not dominate, it contributes. Understanding this contribution matters for interpretation. Measurements made on the lunar surface reflect a mixture of influences. Some oxygen originates within the Moon's own materials, some arrives from the solar wind, some comes from Earth. Separating these sources requires understanding how each behaves when it interacts with regolith. Oxygen from Earth arrives under specific conditions. It is associated with passages through the magnetotail. Its energy and charge states reflect that environment. This makes it possible in principle to distinguish Earth-derived oxygen from other sources, not by looking for large deposits, but by identifying subtle patterns. The Moon's lack of atmosphere and slow surface change make this possible. Once oxygen is implanted, it can remain for extremely long periods. Unlike Earth, the Moon does not recycle its surface quickly. There is no rain to wash material away, no plate tectonics to bury or renew layers. Time accumulates on the surface. As a result, the lunar regolith becomes a recorder of its environment. Each interaction leaves a faint mark. Together, these marks form a history. Oxygen drift contributes one chapter to that history. It links the chemistry of the Moon's surface to processes taking place near Earth. This connection does not require large transfers of material. It relies on repetition and stability. Over deep time, the Moon's surface becomes familiar with Earth's extended environment. It reflects not only what happens on the Moon, but what happens around Earth as well. Understanding oxygen interaction with regolith clarifies how the Moon has evolved chemically. It also provides context for future measurements and experiments. The Moon is not simply a passive object in space. Its surface is shaped continuously by its surroundings. Oxygen arriving from Earth is part of that shaping. Quiet, persistent, and detectable only when viewed across long spans of time. Picture the Moon's surface at rest. No wind, no sound, no movement you could feel. Grains of dust lie where they have settled for immense spans of time. Nothing disturbs them quickly. Above this surface, particles arrive silently. One by one, they make contact. There is no pattern you could see in the moment. Each encounter is brief. Each change is small. Energy transfers quietly. Atoms shift position. Charge dissipates. Then stillness returns. This repeats again and again, day after day, orbit after orbit. The Moon does not respond. It does not adjust or recover. It simply records. Over long periods, these tiny changes accumulate, not as visible layers, but as altered probabilities within the material itself. Grains become slightly different from what they were before. Defects persist, bindings remain. Time is the active ingredient. Without time, nothing would matter. With enough time, everything leaves a trace. The surface becomes a memory without awareness, a record without intention. From a distance, the Moon looks unchanged. Up close at the scale of atoms, it carries a quiet history. This is how interaction unfolds on an airless world, not through events, but through persistence. Each particle that arrives becomes part of a larger story, a story written slowly without emphasis. The Moon waits without waiting, motion passes over it, and in that passing information remains. This stillness is not emptiness, it is capacity, a surface able to hold traces for as long as conditions allow. In that capacity, the Moon becomes an archive of its environment shaped by countless silent encounters preserved by time alone. To understand why oxygen drift matters, it helps to think in terms of records rather than events. Some environments erase change quickly, others preserve it. Earth belongs to the first category. Its surface is active and restless. Wind-water ice biology and tectonics constantly reshape it. On Earth's surface, chemistry is temporary. Traces left by particles or radiation are often removed, buried, or transformed within short geological times. History on Earth is stored deep underground. It is locked into rocks that have been shielded from surface processes. The Moon is different. Its surface is exposed, stable, and slow to change. There is no atmosphere to drive weather, no liquid water to transport material, no plate tectonics to recycle the crust. As a result, the Moon's surface becomes a long-term archive. It accumulates information rather than erasing it. Each interaction with space leaves a mark that can persist for immense spans of time. Radiation alters crystal structures. Particles implant atoms. Micrometeoroid impacts fracture grains without resetting them. Oxygen ions arriving from Earth become part of this process. They do not stand out as dramatic additions. They blend into the background of ongoing exposure. What makes them important is not how much arrives, but how reliably it happens. Earth-derived oxygen reaches the Moon repeatedly under similar conditions. Over millions of years, this repetition produces patterns. Not visible patterns, but chemical and isotopic distributions that differ slightly from other sources. Scientists studying lunar regolith look for these kinds of signals. They analyze ratios, bonding states, and spatial variation across samples. These measurements allow researchers to infer long-term exposure histories. They reveal what kinds of particles reach the surface and under what conditions. Oxygen from Earth contributes to this history in a distinctive way. Its arrival is linked to Earth's magnetic environment rather than to the solar wind alone. This means the Moon's surface contains information about Earth's near-space conditions. Not just about the Moon itself, but about how Earth interacted with space over time. In this sense, the Moon records more than its own story. It records the behavior of its larger neighborhood. This perspective shifts how we interpret lunar data. Measurements are no longer snapshots. They become pages in a long narrative. A single sample reflects countless encounters. Each grain of regolith has been modified again and again. No individual oxygen ion matters by itself. Meaning emerges only when interactions are viewed collectively. This is how a faint process becomes readable. Persistence turns subtle change into measurable signal. The Moon's slow surface evolution makes this possible. Once implanted atoms can remain in place for extremely long periods. There is little to disturb them, only rare impacts and gradual radiation damage. Because of this stability, the Moon functions as a reference surface. It preserves conditions that would be erased elsewhere. Oxygen drift fits naturally into this framework. It is not an anomaly that disrupts interpretation. It is one of the processes that interpretation must account for. By reading the Moon as a record, scientists can reconstruct interactions that cannot be observed directly. They can infer how particles moved through space long ago. This transforms oxygen drift from a curiosity into a tool. It becomes a way to study Earth's extended environment using the Moon as evidence. The record is not perfect. It is influenced by many overlapping processes, but it is stable enough to hold information that would otherwise vanish. In this way, the Moon serves as a quiet witness. It does not react, it preserves. Understanding how to read this record allows small, slow processes to take on larger meaning. What drifts invisibly through space can leave a permanent trace when time is allowed to accumulate. Imagine time passing without interruption. No seasons, no cycles you could feel, only steady exposure. The Moon's surface remains still. Nothing sweeps across it, nothing resets it. Particles arrive quietly, radiation passes through, micrometeoroids strike and move on. Each interaction is small, none announces itself. Yet nothing is undone. Grains of regolith sit where they formed. Atoms displaced by energy remain displaced. Bindings persist. Change does not disappear here, it accumulates. This is what makes the surface readable. Not because events are large, but because nothing erases them quickly. Time becomes a lens. What is faint in the moment becomes clear across duration. The Moon does not hurry, it does not respond. It allows interaction to leave its mark. Day after day, orbit after orbit, the same processes repeat. Some variations occur, most conditions remain similar. Still, exposure continues. Particles from different origins arrive under different circumstances. Each leaves a slightly different imprint. Over long periods, these differences separate into patterns. Not sharp boundaries, but subtle distributions. The surface holds them without judgment. It does not distinguish importance. Everything is preserved according to persistence. This is the opposite of motion driven by urgency. Nothing competes. Nothing dominates. Only consistency matters. From far away, the Moon looks unchanged. From the scale of atoms, it is layered with history. This stillness is active in its own way. It allows information to remain accessible. Where Earth forgets, the Moon remembers. Not through intention, but through absence of disturbance. In that absence, traces remain. and with enough patience those traces can be read. Here motion becomes history, and quiet processes become meaningful simply because time is allowed to do its work. Understanding oxygen drift is not only about reconstructing the past, it also shapes how the moon should be approached as a place of long-term scientific activity. The lunar surface is often described as simple, airless, dry and inactive. In reality, it is an environment continuously shaped by its surroundings. Charged particles, radiation and micrometeoroids interact with the surface every day. These influences operate slowly, but they never stop. Oxygen drift adds another layer to this environment. It connects the moon chemically to Earth's extended space system. This matters first for measurement. Instruments placed on the lunar surface are designed to detect small signals. Their readings depend on the chemical and physical state of the material they touch. If surface oxygen comes from multiple sources, those sources must be understood. Otherwise, measurements can be misinterpreted. Oxygen originating from the moon itself behaves differently from oxygen implanted by the solar wind. Oxygen arriving from Earth carries a distinct history tied to Earth's magnetic environment. Distinguishing between these contributions improves accuracy. It allows scientists to separate local processes from external influences. This distinction becomes increasingly important as experiments remain active for longer periods. Short missions may never notice slow background effects. Long-duration studies cannot ignore them. Surface chemistry influences how materials age. Dust behavior, electrostatic charging, and interaction with radiation are all affected by what the surface contains at the smallest scales. Even subtle changes can matter when systems are expected to operate for years rather than days. Understanding oxygen drift provides context for these conditions. It explains why the moon's surface cannot be treated as chemically neutral or unchanged over time. This perspective supports careful experimental design. It encourages measurements that account for background processes rather than assuming ideal conditions. Beyond instrumentation, oxygen drift also informs how samples are interpreted. Material returned from the moon reflects a history of exposure. Knowing that some oxygen originates from Earth helps place those samples within a broader framework. It prevents over-attribution of features to purely lunar processes. As activity near the moon increases, this understanding becomes more valuable. More instruments mean more sensitivity to subtle effects. More time on the surface increases cumulative exposure. The moon is becoming a place of sustained observation rather than brief visits. That shift requires attention to slow processes that would otherwise be overlooked. Oxygen drift represents one of those processes. It is not dramatic. It does not dominate the environment. Its importance lies in persistence. By recognizing this, science on the moon becomes more precise. Measurements gain context. Long-term trends become interpretable. This understanding also reinforces a broader principle. The moon does not exist in isolation. It is part of a shared environment shaped by Earth and the Sun. Its surface responds to that environment continuously. Planning future investigations with this in mind improves reliability. It aligns expectations with physical reality. International collaboration plays a role here. Different approaches to instrumentation, robotics, and surface science contribute to a more complete picture. Understanding the lunar environment benefits from multiple perspectives and long-term commitment. Slow processes require sustained observation. Oxygen drift highlights why patience matters in space science. Not everything reveals itself quickly. Some processes only become visible when measured consistently over time. By accounting for oxygen drift, future lunar science can avoid blind spots. It can interpret signals with greater confidence. The moon's value as a scientific platform depends on understanding its background conditions. Quiet influences shape every measurement made on its surface. Recognizing those influences turns subtle processes into practical knowledge. Oxygen drift does not change how the moon looks. It changes how the moon should be understood. And that understanding becomes increasingly important as human and robotic presence continues to grow. Oxygen drift between Earth and the moon is not an isolated case. It reflects a broader principle about how planets exist within space. Planets are often imagined as self-contained worlds, each with its own atmosphere, surface, and boundary. In practice, those boundaries are gradual rather than absolute. Atmospheres fade with height. Magnetic fields extend far beyond visible surfaces. Particles move through regions shaped by forces that do not stop at planetary edges. This creates a different picture of planetary systems. Worlds are not sealed objects. They are centers of influence embedded within larger environments. Matter moves slowly between these environments, not in dramatic exchanges and not in large quantities, but through persistent low-level motion guided by structure. Oxygen drifting from Earth toward the Moon demonstrates this clearly. A planet with a strong atmosphere can still contribute material to its surroundings without instability. The key is duration. Processes that operate continuously over millions and billions of years do not need intensity to matter. This principle applies throughout the solar system. Charged particles move between planets, moons, and interplanetary space. Their paths are shaped by magnetic fields, radiation, and gravity working together. What differs from place to place is not whether exchange occurs, but how it is organized. Each planet shapes its surrounding environment in a unique way. Earth's magnetic field creates one such organization. It guides motion near the planet and extends influence far into space. The Moon becomes part of this system simply by moving through it. No special alignment is required beyond orbital motion and time. This way of thinking replaces sharp divisions with continuity. Atmosphere becomes near space. Near space becomes structured plasma. Structured plasma interacts with surfaces. Oxygen drift fits naturally into this continuum. It is neither anomaly nor exception. It is an expected outcome of long-lived physical conditions. Understanding this helps unify different observations. Atmospheric escape, magnetospheric structure, and surface chemistry are not separate topics. They are linked parts of a single process unfolding across scales. This perspective also reframes stability. Stability does not require isolation. A system can remain stable while still exchanging trace material with its surroundings. Earth retains its atmosphere, the Moon remains airless, yet connection exists. That connection does not weaken either body. It enriches understanding of how planetary environments behave over time. Oxygen drifting toward the Moon shows how influence extends beyond surfaces. A planet leaves traces not only through gravity and light, but through matter moving slowly outward. These traces are subtle. They require patience and careful measurement to detect, but they are real, and they carry information about the conditions that produced them. Seen this way, the Earth-Moon system becomes an extended structure. Not fused, not separate, but linked through persistent motion. This principle reaches beyond Earth and Moon. It applies wherever fields guide particles and time allows motion to accumulate. Planetary systems are defined as much by their environments as by their surfaces. Oxygen drift is one expression of that definition. A quiet example of how worlds remain connected even across empty space. Imagine space not as emptiness but as continuity. A place where influence fades slowly rather than ending. Earth turns quietly below. The Moon continues its orbit. Between them, motion persists. Particles move without urgency. Fields shape paths without effort. Time carries everything forward. Nothing announces these processes. They do not arrive as events. They unfold as conditions. Above the atmosphere, oxygen becomes something different. No longer breath, no longer wind. Just matter responding to structure. Farther out, magnetic shape replaces gravity as the guide. Motion slows curves and stretches. The Moon passes through these regions again and again. Each passage feels the same. Each passage adds another moment of contact. No single crossing matters, only repetition. At the surface, particles arrive quietly. They interact transfer energy and remain. The Moon does not react, it does not erase, it holds. Time deepens, traces accumulate. What began as motion becomes record. What was invisible becomes readable. This is how connection works at planetary scales. Not through force, but through persistence. Worlds influence one another without touching directly. They share space structure and time. From far away, nothing seems to change. Up close, everything is shaped by slow interaction. Earth and Moon continue as they always have. One active, one still. Both part of a larger environment. The drift never stops completely. Fields remain. Time continues. And within that continuity, small motions link large systems. This is a story of trace transfer and relationship. A quiet link shaped by fields and time. Exchange can occur at trace levels. The rest of the system continues as usual. In space, connection rarely announces itself. It reveals itself only when patience allows it to be seen. Given enough time, even the faintest motion leaves a trace, and those traces held without urgency become the record of how worlds remain connected across the dark.